Welcome to the course Business Analytics and Data Mining Modeling using R. So we have come to our last technique that we want to discuss, that is discriminant analysis. So let's start. So discriminant analysis is also a statistical technique typically used for classification or profiling tasks. So application and the different types of tasks that it could be used are quite similar to what we discussed for a logistic regression. So this is also a model based approach. So typically we make assumptions about the structure of relationship between outcome variable and set of predictors. So model based approach. If we look at the main idea behind discriminant analysis, so you can see 2 points. So two approaches have been used to conceptualize the idea of discriminant analysis. First one is to find a separating line or hyperplane equidistant from centroids of different classes. So by this you can also understand the main application, mainly discriminant analysis is used for classification task. So let's read it again. To find a separating line or hyperplane equidistant from centroids of different classes. So from this we can understand that we are talking about, when we discuss discriminant analysis, we are essentially looking for a separating line. So this particular technique is about finding a separating line which is equidistant from centroids of different classes. So let's say centroid for this particular group is this one, and centroid for this particular group is this one. So probably we are looking for a line which is equidistant from the centroid of different classes. So sometimes this approach is used to implement discriminant analysis. Another approach is to find a separating line or hyperplane that is best at discriminating the records into different classes. So that is another approach. So in terms of theoretical understanding, there is not much of a difference. However, when you go about implementing it using software, implementing the actual steps of algorithm, then there is slight differences. So the second approach is to find a separating line or hyperplane that is best at discriminating the records into different classes. So in that sense, we are looking for a particular line or hyperplane that might be best at discriminating these cloud of observations, right, into their respective groups, right. So these are the two approaches. First one, finding a equidistance finding an equidistant line or hyperplane. So that would of course because that is equidistant from centroids of these groups, so probably that would do a good job of classification. The second one is finding a line that would be best at discriminating the records into different classes. So these two approaches are popular in discriminant analysis and have been implemented. So the classification procedure that is used here is based on distance-based metrics. So few distance-based metrics we have covered when we discussed KNN, and so this particular technique is also based on distance-based metrics. So the main idea is again based on the distance of a record from each class. So as you can understand from the two approaches that we discussed, the underlying computation calculation that would be required in each of those approaches would be calculation of distance of a record from each class. So this calculation then becomes the basis for classifying observation. So let's move forward. So classification, few more points are there. For example, best separation between items is found by measuring their distance from each class. So for different items that are there, So how we can separate them into their respective groups. So that is found, as we talked about, measuring their distance from each class, and particular item is classified to the closest class. So we measure the distance of a particular item from each class, and and then depending on its closeness to a particular class, so the particular item is accordingly classified. So next important point is what are these distance metric that could be used. So one option to use a Euclidean distance metric for discriminant analysis. So we are already familiar with this. This is the formula for a Euclidean distance metric. Distance of a record, let's say x1 to xp. So we have p predictors. So we'll have these p values in for this p values in this. So distance of a record x1 to xp from centroid, x1 bar to xp bar of a class is computed in this fashion. So this distance EU, that is for Euclidean, and distance between x, that is for an item for a record, and distance from the centroid, that is x bar. So that is nothing but vector of means of p predictors, as you can see, where centroid x bar is a vector of means of p predictors. So formula is quite familiar, square root of x1 minus x1 bar square, then up to xp minus xp bar whole square. So this is the formula, and this can be used as a distance metric for those calculation for each item and its distance from each of those classes, and then finally classification based on those computations. So Euclidean distance metric is one that could be used, but as we have discussed before as well in Canaan as well, that there are a few issues with the Euclidean distance metric. So let's understand them. So first one is that distance values depend on the unit of a measurement. So as it is very clear from the formula itself. So if we have two variable, one is being measured on square feet, and the another one is being measured on hundreds of square feet. So of course the actual values are going to be different, but those values, when they are used in Euclidean distance metric, one particular variable would dominate the distance. So therefore distance values that are going to come, they are going to be dependent on unit of measurement. So that is quite problematic in sometimes in some data sets. So that is one problem. Second one is based on mean and doesn't account for variance. So we look at the Euclidean distance metric that we just saw. We are trying to compute the distance of a particular item, particular record from centroid of each of the classes. So therefore those now centroid is a vector of means for all predictors. Then therefore the distance computation is actually just accounting for mean values, and we are not accounting for variance. Now variability might play sometimes an important role in determining the closeness of a record to a particular class, right? Because if the computation is based on just this, but the variability is not accounted. So one class might have a larger spread, a higher variability. So because of that larger spread, also a new observation is likely to be closer to this class, despite the distance between mean and that new observation might be on the higher side, but because of the variability, the spread, more likely that a particular new observation could belong to this class. However, even though the distance would be smaller from this lower variability group, as per the Euclidean distance metric, that a new observation might be assigned to this group. However, higher spread, so probably there is a good chance that new observation might go to this group. So variability is an important variability plays an important role in determining the closeness of a record to a particular class. Let's say this is the observation, new observation, and we can see this is the distance from this centroid, and this is the distance from this particular centroid. So if we look at it, this distance is smaller. So therefore, as per the Euclidean distance metric, probably this record is going to be allocated to this group. However, if we look at the spread of this group, this spread is much wider. So this point is quite close to this sphere. However, it is slightly more distant to this this sphere. So because of that. We can say that there is another argument could be there, that this observation, if we'll just look at the variability or spread, then probably this observation can also belong to this particular group. So as per the variability observation, this new observation can go to this group, but if we look at just the distance from the centroid, that is accounting for mean, this observation will go to this group. So therefore, mean and variance both should be accounted, so which is not the case with the Euclidean distance metric. So apart from the scale dominance, and the variance is also an issue on Euclidean distance metric. So to eliminate these two problems, we can think of distance can be computed using standard deviation z-score, that is z-score, instead of unit of measurement. So instead of using those actual values, even if they are in different unit of measurement, we can actually go for measuring them in terms of standard deviation. So therefore, that means z-scores. So that would eliminate the first problem, the scale dependence, and the second problem also would be covered, because the standard deviation, which is also an indicator for the spread, would also be part of this process. So that is one way we can overcome these two problems. However, there is one more issue with Euclidean distance metric, is that correlation between variables is ignored. So these variables that are going to be the part of the process of this distance calculation. So the correlation is also important. So that is also ignored in Euclidean distance metric. So how do we solve this one? Because correlation relationship between different, because this one is more like a 2D space. When we talking about p predictors, we are into p dimensional space. So therefore, the correlation between two variables might also play an important role in terms of determining the closeness of a record to a particular group. So this particular issue should also be resolved. So the next distance metric, that is called statistical distance or Mahalanobis distance, that can be used to overcome the issues that we have discussed, with Euclidean distance metric. So the statistical distance or Mahalanobis distance is typically defined as below, as you can see in the slide. DML, that is ML for Mahalanobis distance, then the distance of a record X from centroid of a class X bar can be computed in this fashion: X minus X bar transpose, and then we have S inverse, then X minus X bar. So you can see that X minus X bar transpose, this is transpose matrix of X minus X bar. So essentially the column vectors are turned into row vectors, and then we have S inverse. So this is the inverse matrix of X. So this can be thought of, this is where S is a covariance matrix between P predictors. So see in the definition itself, covariance matrix is part of this calculation, the statistical distance calculation. So therefore, correlation between predictors that is accounted, and you can see that the S inverse, this can also be considered as a p dimensional extension of division operation. So in this fashion, scaling is also part of the process. So if we take this particular statistical distance formula to one dimensional space, you would also realize that this formula would convert into a Z score for one dimensional space. So we would see that some of the two important issues, that scale dependence and the variance that we could overcome using Z scores, are part of this formula, because this is for n dimensional or specifically p dimensional space. So this is also is overcoming the taking the same advantage. You can say extension into p dimensional space, and because S is there, so which is covariance matrix. So correlation, the another issue that was there with Euclidean distance matrix, that is also overcome using this statistical distance. So covariance is so correlation is accounted using the covariance matrix, and since we are taking inverse of it, so scaling is also accounted, and since we are scaling is also accounted, since we are taking the subtraction from mean values, that is centroid. So and then scaling is also accounted. So scale dependence is also considered, variability and other things are also accounted for. So this statistical distance matrix, Mahalanobis distance matrix, that seems to be a much better metric for distance calculation in discriminant analysis. So next important point is about how some of these things are implemented. However, we have talked about the discussion that we had about the discriminant analysis. It was mainly based on distance, computing a distance of a new observation from each of the class, and then assigning it to the closest class. However, the implementation is done using linear classification functions, and that also brings about the similarity of discriminant analysis with multiple linear regression. So let's discuss this aspect. So linear classification functions are used to implement some of these things that we talked about, the distances and other things. So used as basis for separation of records into classes. So these functions are used as basis for separation of records into classes, and these functions compute classification score measuring closeness of a record to each class. So something that we discussed, that distance matrix are used, and this is classification function actually implement the same thing in a functional form. So distance idea in a functional form is implemented. So you can see first point here, compute classification score measuring closeness of a record to each class. The second point is highest classification score is equivalent of a smallest statistical distance. So we would see the main idea that was based on using the distance matrix is actually captured here in linear classification functions. So but the implementation is now different. So instead of measuring the distance, calculating the distance, we actually use these classification functions to compute classification score. However, in terms of understanding and interpretation, the main idea, the main underlying basis is same. So instead of saying smallest statistical distance, we would be saying is highest classification score. So again, to understand what these functions do, next point is, so main idea behind these function is to find linear functions of predictors that maximize ratio of between class variability to within class variability. So you can see when I said that linear classification functions bring discriminant analysis closer to what we understood in multiple linear regression, you can see that here also we are looking for a linear functions of predictors. So these classification functions, they are actually linear combinations of linear functions of predictors. So in that sense, the similarity with the multiple linear regressions, and later on we will also discuss some of the application and performance of discriminant analysis are also quite similar to what we discussed in multiple linear regression. So the idea is to find these linear functions predictors that maximize ratio of between class variability to within class variability. So therefore, if the between class variability is between these two classes, for example in this two class case, so a ratio of this, so this variability and divided by within class variability, so that means we are trying to separate these groups. So this ratio would indicate, so if this ratio is maximized, so therefore we are trying to achieve maximum separation between these groups, and we would be able to discriminate between observations and will be able to classify them to their respective groups. So through maximization of this ratio, these functions are determined. So these linear functions are predictors, they are determined using by maximizing this ratio, and the underlying understanding is quite similar to what we discussed. The distance based calculation, instead of distance based calculation will have the classification as scores, but the idea is coming from that. So to understand a few things what we have discussed till now, let's go back to our studio, and through an exercise we'll try understand few of the points that we have discussed. So the data set that we are going to use right now is Sedon data set that we are already familiar with. So let's load this package XLSX. So let's import the data set. Let's remove any columns, any rows. So these are the three variables that we already are familiar with: annual income, household area, ownership, and this is the structure of the data frame. Annual income and household area are numeric, and ownership is the factor variable, categorical variable. So that is also our outcome variable in this case. So we have two groups, as you can see, non-owner and owner. Now first important aspect that we discussed that we need to discuss is the class separation into classes. So it is important for a particular classification model to do well in classifying observation, that class separation is should be a bit more clear. If class separation is clear, then a particular classification model would probably do a good job of classifying the observations. However, if the class separation is not clear, then in that case the modeling would be much more complicated and the performance would not be as expected. So let's understand these two things using some plots here. So this plot which is quite similar to the example that we have shown here in the board. So let's plot this. So these are the observations. This is the scatter plot. So as you can see here, this particular group is top right group. This is owners group, and then bottom left group, this is the non-owners groups. So there is clear separation between these two groups, and therefore it is easier for any classification model to separate observation into their respective groups. So if the class separation is clear, then probably the classification would be much easier. So we can find a so discriminant analysis, that main idea that we talked about, that finding a line or hyperplane that is either equidistant, so that was one approach, or finding a best line or hyperplane that does the good job of discriminating the observations. So let's try and find out a line. So if we look at this scatter plot, if we we draw a line somewhere from here to here, you would see we will get a good enough separation where only one observation would be misclassified, as we can see here. So this is the point that we want to locate. You can see this is between 20 and 22 on y axis, and between I guess 5 and 6 along x axis. So this point we want to locate. So our our line would come above this particular point. So let's find out. So this is one way to find out, because we are doing some manual process here, following manual process to find that line. So we can see 20 to 22 and 5 to 6. So you can see annual income 5 to 6 and household leader 20 to 22. So we would be able to find probably this point. So you can see this is the point 5.3 and 21. So this seems to be the point 5.3 and 21. So this is the point. So let's find out another point on this in this particular zone. So this seems to be the point. So our line should be our discriminant line should be below this particular line. So as I suggested, the line could go like this, and therefore it should be below this point. So let's find out this point. This point seems to be between 8 and 9 along x axis, and between 16 and 18 along y axis. So you can see here 8 and 9 here, annual income along x axis, and 16 to 18 along y axis. So let's find out this particular point. So you can see 8.5 and 17. So this seems to be the point 8.5, about 8.5 and 17. Now our we can now manually assign some coordinates to draw our line. You can see here we are plotting a line from 5.3 to 22. So the point was 5.3, 21. So we are moving up in the y direction. So 22 value therefore, and the second point is 8.5 and 17. So again we are moving down along the y direction. So the x value is same 8.5, and the value is from 17 here to 15 now. So we will get a line, a separating discriminant line. So let's plot this. We can see. So probably this could be, so through our manual process visual inspection, we can see that this could be one line that that would be able to discriminate the observations into their respective groups. So this also seems to be equidistance line from the centroid of these two groups. So both these approaches, typically the line that we get typically is going to be same. So we can extend this line using few lines of codes here. So you can see using these two coordinates, these point coordinates that we have identified, we can compute slope, and we can use this slope to extend this line further. As you would see, the line is being extended in the plot. So let's look at, you can see this line has been extended. So this is the line that we were talking about. So the main idea about discriminant analysis is to find this line that would be able to separate these observations. So from this it is also clear that we would like to have the class separation. So the class separation should be quite clear for discriminant analysis to probably work well. So let's look at another example where this class separation is not quite clear. So this is Pomo offers data set. So we are also familiar with this one as well. So let's import this one and let's see what is the scenario in this particular data set. So in this particular data set, as we would see that the observations belonging to different groups, they are not there is no clear separation between those groups, and that would actually complicate the performance of the model. So let's remove any columns, any rows. Let's change the palette, and we are taking these 200 observations. And using these two observations, now we are again using log scale here. So because there are too many observations, so and they are within one particular limited coordinate area, so they would be so we would like to space them out. So that is why we are using log scale here. So these are the observations. So let's look at. So, in this particular case we can see here that even though we have used only 200 points, we can see that both the groups, they are lying all around in the similar area, and we can see that separation is quite difficult here. Similarly, if we plot, if we use all the observations instead of this sample, so let us look at all the observations. So, if we look at all the observations, this situation is even more difficult. You can see here. Here you would see that this particular hop, top right hop, we see that observation belonging to both acceptor and non-acceptor class are clubbed in there. So, it is going to be quite the class separation is not quite clear in this particular region. However, this particular hop, the mid part and the this left part, most of the observation belong to the non-acceptor groups. So, these are low hanging fruits, and model would be able to correctly classify these observations because they typically belong to just one class, one group. However, this top right group, this is quite complicated, the separation is not clear. So, if the separation is not clear, it is going to be difficult for a model to give a good performance. Now, you would also see for any model that we apply on this particular data, typically the performance of that model would come out to be quite good. That is because the majority of the observation are very easily going to be classified. You can see here so many observations are here and which are going to be easily classified as non-acceptor. So, overall performance of the model would be quite good, but if we restrict ourselves to this part, probably the performance of the model would be under would be tested on this part, how, because the class separation is not that clear. So, with this we will stop here, and in our next lecture on discriminant analysis we will do modeling. We will build our discriminant analysis model using the Sidon-Carr data set. Thank you.